Okay, so Venn diagrams and two-way tables are just two different ways of displaying the same amount of data. So it's going to be when you have multiple variables, usually categorical. And so this is an example where I say, okay, I've taken a sample of people and I focused in on these two variables, their gender and their pierced ears status, right? So whether or not they have pierced ears. And so I sampled everybody, I surveyed them, and I created basically a two-way table out of this. And I defined event A as is male and B as has pierced ears. And so for A, they say find the probability that a student has pierced ears. So for part A, they just want the probability of event B occurring, right? And so in general, they're talking about all students. So the total number of outcomes then would just be the total number of people we surveyed. So that's 178. And then I would just want to look for the total that have pierced ears, right? And so the total that have pierced ears is going to be that. Remember what we call that? That's a marginal distribution. That's the totals and the margin. So that's just 103 out of 178. All right. So B, find the probability that the student is male, which is event A, and has pierced ears. Probability of A and B. So we're still talking about the same population. So it's still going to be out of the same 178 total students. But now we're narrowed down within our table. So we want them to be both male and have pierced ears. So that's going to be the overlap of the male row and the yes pierced ears column, right? And so you can see that here, male and pierced ears. So there's only 19 of those. That's just 19 out of the 178. All right, so C, here's where it gets a little dicey. What about the probability that they are male or have pierced ears? So that's A or B. Now, if the events are mutually exclusive, right, in the last section we said we're allowed to just add their individual probabilities. But are these events mutually exclusive? Meaning, cannot occur at the same time. No, these can occur at the same time. In fact, we found that they do in part B, right? There are males that have pierced ears. So the idea here is that we're going to have to account for that fact. If I go, okay, well, let's just add together the probability that they are male. So the probability that they are male is what? It's out of 178. How many total males are there?
90.
Yep. So the probability that they're a male is 90 out of 178. And if I go, okay, what's the probability that they have pierced ears? Well, that's what we calculated in part B. That's 19 out of 178. The problem with that is, oh no, that's not 19 out of 178, I apologize. Pierced ears is out of 178. What's the total number of people who have pierced ears?
103.
Yeah, that's the 103 out of 178. The problem is that males with pierced ears got counted in both of those, right? They got counted in both, so they got double counted, essentially. So what we want to do is subtract off that overlap once. So we want to subtract off the probability of males that have pierced ears, which is going to be that 19 out of 178. Because that 19 out of 178 got counted in both of those initial ones, and we only want it counted once, right? So we're going to subtract off one occurrence of that, which is then going to give us our final answer. So 90 plus 103 minus 19. And that's going to give us the 174 out of 108. Does that make sense? All right. And here is your general addition rule for two events. So write this down, just what's in the table here. So now we can generalize that rule we had before. Before we only had an addition rule if they were mutually exclusive. Now, even if they're not mutually exclusive, what we do is add the probability of event A to the probability of event B, and then we just subtract off the probability of event A and B. So we subtract off the overlap that occurs in both A and B. That way it only gets counted once, right? This formula even works for mutually exclusive events. It's just if the events are mutually exclusive, what will this probability be? If they're mutually exclusive, what's the probability of both events occurring simultaneously? Right, exactly. Thank you, Grace. It's just 0. So then that just reduces to just probability A plus probability B like we saw before. Oh, damn it. There we go. All right, so filling out Venn diagrams, you can do that from a two-way table. You can kind of see how this Venn diagram is labeled with each part of the two-way table. You can fill out two-way tables, or sorry, Venn diagrams in two different ways. You can either label each piece with a probability, or you can label it with the number of outcomes. And either way is pretty acceptable. And I'll kind of show you what I mean here. All right. So generally the circles in a Venn diagram represent events that we're interested in. You always want to put your circles inside a rectangle, which we call the universe. It's the universe that you're interested in. So that's going to consist of your sample space. All right, so if the inside of the circle represents event A, then what's outside the circle but still inside your universe is the complement of A. If you have two disjoint or mutually exclusive events, that means that in a Venn diagram they won't overlap because they have no outcomes in common. Okay. The intersection of events A and B, so if events A and B are not mutually exclusive, then they will overlap. In terms of the diagram itself, you don't need to make the size of the overlap proportional to how much they occur in common. That does not matter, right? If they overlap, that just means they have some events in common. So A and B is illustrated by the shaded area there. That's where they intersect. A or B is illustrated by the shaded area in the bottom one, which is everything inside both circles, including the overlap, right? And those symbols the sort of upside down horseshoe is and the horseshoe that looks like a U is U. And they stand for union for or and intersection for and. Okay, folks, here's what I'm going to do. All right, so what we're going to do is take a look at a couple examples, just going from data and or two-way tables into a Venn diagram. So if we look at the pierced ears example, we had that two-way table. If I wanted to label the Venn diagram, and when you create a Venn diagram for a two-way table, you want to make sure you label every part of it. Here's an example where they label the Venn diagrams using counts instead of probabilities. Like I said, either one is relatively acceptable. So they're actually labeling the count of each section rather than putting a probability in each section. So remember, event A represents, oh boy, I don't remember. Event A is male and B has pierced ears. All right. So the yellow circle represents event A and the blue circle represents event B. So if we look at the overlap between those, the 19, those are males with pierced ears, so they're going to be in the intersection. And then outside of the circle would be just males without pierced ears, so that's the 71. You can see that the total inside event A is 90 if you add the 71 to the 19. So event B has pierced ears. This section, the just light blue, would represent non-males with pierced ears. So in this case, females with pierced ears would be 84. And total number of females is 88. Or sorry, total number, rather, with pierced ears should be 103. Right, and then what's outside of these events would be non-males without pierced ears, aka females without pierced ears, and that's just 4. All right, so let's take an example from start to finish and look at a two-way table and a Venn diagram that'll represent this data. So what is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the 2000 census was chosen. Each member of the sample was identified as a high school graduate or not, and a homeowner or not. Overall, 340 were homeowners, 310 were high school graduates, and 221 were both homeowners and high school graduates. So what I'm going to do is create a two-way table and convert that to a Venn diagram. So what we're going to do is look at our two variables of interest. So I have graduation status, and I'm going to up here have home ownership status. And for both of those, I'm just going to either say yes or no, meaning yes, they graduated high school, or no, they did not. For these, same thing. Yes, they own a home, or no, they do not. Okay. All right, so looking at, and I'm gonna get a section for our marginal distributions here. So we should have 500 in total, right? Okay, 340 were homeowners. So that 340 is going to go down here. That's the total number of homeowners. 310 were high school graduates. So that's 310. That's the marginal distribution for high school graduates. So right away, we can fill in the rest of the marginal distributions because we know they have to add up to a total of 500. So this is going to be 160 were not homeowners, and 190 did not graduate high school. All right. 221 were both homeowners and high school graduates. So it's 221 here. Now we know vertically that needs to add up to 340, so I can just subtract 221 from 340. And it tells me that 119 were homeowners but not high school graduates. And across, I know that 221 plus whatever this value is has to add up to 310, so I can do a subtraction again. 310 minus 221. I get 89 here. And again, vertically, 160 minus 89 gives me 71. We can just verify that across 119 plus 71 does give me the 190, so it's correctly filled out. Great, so there's my two-way table. What I want to do is convert that to a Venn diagram. Now, to do that, we have to make a decision, because in a Venn diagram, you're just going to focus on one value of each variable. So it doesn't matter which, you can have your Venn diagram communicate that information regardless of which value you have. So I'm going to do this. I'm going to let event, let's call event A, they're a homeowner. And we'll call event B, they graduated high school. All right, so we're going to do this. We're going to have event A, and we know that they overlap with event B. We're just going to fill in the values. And so how many people here, we know that total homeowners were 340, but if I want to just fill out in this section, that's homeowners that did not graduate high school. So that's going to be just your 119. And then the overlap is homeowners that did graduate high school. So within that, we're going to have our 221. You can see that that should add up to the total number of homeowners, which is 340. Oops. And then event B, graduated high school. Well, I know that that's a total of 310, but the section here is graduated high school but are not homeowners, so that's only going to be, right, 89, but the 221 plus the 89 should give me the 310, which it does. And then the outside, remember this section is they're neither a homeowner nor did they graduate high school. So neither a homeowner nor graduated high school, which is 71. You always want it such that your total of all these numbers should add up to your total in the table, which is 500, right? And these do. So if I do 119 plus 221 plus 89 plus 71, I end up with 500. All right. So here's an example where you're actually giving percentages. According to the National Center for Health Statistics, in December 2012, 60% of U.S. households had a traditional landline, 89% of households had cell phones, and 51% had both. So if I were going to create a Venn diagram out of this, let's call event A landline, event B cell phone. Okay. And so what I want you to be careful about with something like this is for event A, they specify that 60% have landlines and 89% have cell phones. So notice if you add 60 plus 89, that's more than 100%. So what you want to understand is that when they say 60% had landlines, that does not mean they necessarily only had landlines. They could have also had a cell phone. So that 60% is all of the circle for A, including the overlap. And that 89% is all of the circle representing B, including the overlap. So when they say 51% had both, I'm going to put my 0.51 here. That's the overlap. To figure out what goes into this section, I have to subtract out that 51% from the 89%. So 89 minus 51 leaves me with 38, meaning 0.38 of people only had cell phones. And if I do that same subtraction, 60% minus the 51%, that leaves me with 0.09 only had landlines. And if I add those up, 0.09 plus 0.51 plus 0.38, that gives me 0.98, which leaves me with, out here, 0.02 or 2% of people that don't have either a landline or a cell phone. These are your people who live in the woods with tinfoil around their roofs. All right, so that's 5.2 part 2.